Hello, this is Min Guli from the Open Cloud Platform Center. I will be conducting this webinar on multi-cloud strategy for K-PaaS container platform as the 5th Tech Edge session this year. The presentation order will be as follows: overview of multi-cloud in container platform, and practical exercises on service mesh in a multi-cloud environment. Overview of multi-cloud in container platform, and practical exercises on service mesh in a multi-cloud environment. Please note that today's webinar includes hands-on exercises. Let's first take a look at multi-cloud. This term has become quite common in the cloud industry. Multi-cloud refers to the practice of using services provided by two or more cloud service providers to operate and provide their own services. The cloud service providers referred to here are well-known names like AWS, Azure, GCP, and domestic companies like Naver, NHN, and KT. Multi-cloud is the practice of running applications using services like network, compute, storage. They are provided by two or more cloud service providers. On the right side of the screen, there is a Kubernetes cluster. It's a bit different from the typical setup we imagine. Each node that makes up the cluster is from a different cloud service provider. Can we consider this cluster configured in that way, as a multi-cloud cluster? Yes, of course, it's indeed a multi-cloud configuration. Each node is composed using network services and VMs provided by different cloud service providers. This configuration approach is even recommended as a best practice on the Kubernetes official site. Of course, as I'll explain shortly, when the geographical distance increases, network latency can pose difficulties in service configuration. Therefore, it's common to distribute nodes on a per-zone basis to mitigate these issues. So, why operate in a multi-cloud environment instead of a single cloud setup? There are several advantages. First, avoiding vendor lock-in. This means reducing vendor dependency by utilizing services from various cloud service providers, ensuring cloud portability to prepare for multi-cloud scenarios. Next, competitive pricing. You can compare prices of various services provided by different cloud vendors and make cost-efficient selections. Then, best-of-breed technology adoption. Each cloud has its own strengths and specialized features, so you can use them all. For instance, one cloud provider might excel in offering diverse computing power, while another might specialize in data analysis and AI services. You can segregate these features and offer integrated services. Flexibility and scalability. Distributing application loads across multiple cloud environments can enhance performance, improve user experience, and reduce the risk of data loss by backing up data across multiple clouds. Enhanced risk management. To counteract large-scale outages, which have occurred in the past even domestically, multi's own strategies might not suffice. Leveraging multi-cloud workloads can ensure service continuity. Lastly, robust security. Unique security features from different cloud providers can be used to build multiple security layers, protecting applications and data. Moreover, since these are distributed across different clouds, threats from one cloud won't easily transfer to another, preventing security breaches or attacks from propagating. Now let's explore the trends in multi-cloud support from global cloud providers. The level of support for multi-cloud varies among different cloud service providers, but it hasn't been around for a long time. This is because, from a business perspective, it was more advantageous for companies to encourage the use of their own cloud services. However, now that the adoption of multi-cloud has increased significantly, cloud service providers are also introducing relevant services. Firstly, MS Azure. There is a service called Azure Arc that supports multi-cloud environments and facilitates configuration. Through Azure Arc, various services such as the company's Kubernetes service AKS, VM Compute, Edge modules, and more can be registered for integrated monitoring. Additionally, it offers the functionality to register separately configured Kubernetes or servers provided by different cloud service providers, allowing the use of Kubernetes services from those sources. Furthermore, it provides an environment for integrated monitoring through its own cloud monitoring service. The same applies to GCP. GCP offers a multi-cloud service through Google Anthos, allowing integration of various cloud services similar to Azure, enabling centralized monitoring. To seamlessly consolidate services across different clouds, Meshup is essential. Utilizing Anthos Mesh, developed in-house based on SDO, ensures smooth service interconnection in a multi-cloud environment. Although support for multi-cloud has been slightly delayed compared to other providers, Amazon Web Services, which holds the largest market share in the global cloud market, now offers multi-cloud support. It provides features such as EKS connector to build an AWS environment within on-premise settings, and the ability to connect and utilize services from various other cloud service providers. Domestic cloud service providers are also actively responding to multi-cloud demands. KD has partnered with Microsoft and Oracle Cloud to provide multi-cloud services. NHN offers a Cloud Hub platform as a multi-cloud service, and nCloud continually updates services and materials related to multi-cloud through the Rancher open source platform. Now, I will explain how K-PaaS container platform is preparing for multi-cloud. Currently, the K-PaaS container platform supports multi-clusters. Let's take a look at the architecture. The host cluster in the container platform area supports Kubernetes-based services, such as Istio, Ingress, and Podman, which in turn support Kubernetes services. Additionally, there are services for multi-cluster management such as Portal, Terramin, and Metric API. There are also individual brokers for Cloud Foundry integration, along with various open-source components like Harbor and Keycloak for platform operation. Moreover, the KubeEdge platform supports edge node configuration. Although it's not initially included in the platform, you can register and manage subclusters through platform configurations or creations. For self-monitoring purposes, relevant services can also be installed in the monitoring area. Currently, we have set up subclusters using Terraform and configured them as multi-clusters to enable monitoring. However, the use of Terraform for cluster setup is only supported for AWS and OpenStack. There isn't a specific support feature within the platform for operating applications using multi-cluster capabilities. Hence, we are partnering with domestic cloud service providers to offer an environment for operating applications in multi-cloud environments. To achieve this, we plan to use Terraform to create clusters based on various CSPs and utilize open source tools for service, mesh, and federation to support application configuration in multi-cluster environments. We plan to test these features with various domestic CSPs and aim to provide these services up until the end of this year. Let's now take a closer look at service support in multi-cloud environments, focusing on service mesh and federation. Starting with Istio, it's the most prominent solution for service mesh and a graduated project under the CNCF. Kubeflow and Sidecar have already been installed and are being used in the K-PaaS platform. We plan to showcase various use cases of Istio, including using the Mesh Gateway feature for distributing application services duplexing between multi-clusters. Furthermore, within the container platform package, a dedicated package for multi-cluster deployment will be configured. This will enable us to set up and utilize our portal service in a multi-environment, allowing for versatile applications. Istio is currently widely used in many container-based services and is based on the highly versatile Envoy. However, there is another mesh service that is expected to gain more attention in the future. That is Linkerd. Linkerd is an open-source project developed with a focus on lightweight and lower network overhead for container-based services by incorporating its own sidecar proxy developed in Rust. While we won't be offering a dedicated multi-cluster package for Linkerd like Istio, we will provide guidance on deploying applications in a multi-cluster environment using Linkerd. Lastly, let's talk about Federation. It's an open-source project called Karmata. Conceptually, it views each cluster as a node and binds multiple clusters together to implement container orchestration in a large-scale environment. Within this framework, various services like Istio are utilized for inter-cluster communication. Similarly, there is a community project called OCM, Open Cluster Management, which is a form of bundling and managing multiple clusters centrally as a community project developed based on hub-spoke architecture. We reviewed it, but at the Open Cloud Platform Center, we would like to provide a sample that can operate applications in multiple environments based on Karmata, which is a CNCF project with an active community, by bundling it with Istio service. Next, in terms of the infrastructure as a service aspect, that forms the foundation for effectively utilizing the previously mentioned network services, we aim to facilitate the utilization of domestic cloud service providers within the container platform by offering automated cluster provisioning features based on Terraform. For NHN Cloud and KD Cloud, which both provide IaaS based on OpenStack, we plan to conduct internal testing using the OpenStack provider of Terraform. Subsequently, we will provide infrastructure as code scripts tailored to each CSP and enable automatic cluster creation and management through the Container Platform portal. Naver is also registered as its own provider within Terraform and offers IAC scripts as samples. Leveraging this, we intend to align these capabilities with the multi-cluster development direction of the container platform. Our goal is not only to provide one-time script provisioning for these features, but also to continuously evolve them to suit the multi-cloud environment. Now, let's proceed with a hands-on exercise related to multi-cloud environments. We will demonstrate the operation of service mesh across clouds using Linkerd. As previously explained, the exercise will involve using a sample application to observe how service mesh functions between clouds. We'll utilize Naver Cloud's Kubernetes service and a container platform cluster installed within the OpenStack environment of the Open Cloud Platform Center. The final configuration for the exercise is as depicted on the screen. When making a curl request to Hello World 5000 within the OpenStack environment of the Open Cloud Platform Center, the traffic split API policy will distribute the traffic separately between the Hello World v1 pod of the current cluster and the Hello World v2 service running in NKS, Naver Kubernetes service. This distribution will be observed and verified during the exercise. The practice guide has been made public on the K-PaaS GitHub repository. Let's proceed to the indicated practice guide URL. Firstly, in the OpenStack environment of the first cluster, a cluster of the container platform is installed. The second cluster, marked as number 2, is configured using Naver's Managed Kubernetes Service, NKS. Our provided container platform includes pod security settings by default when utilized on public networks as a security measure. For successful testing during the exercise, you need to disable the pod security settings. Please review and follow the instructions for changing the pod security settings displayed in the material, then proceed. Additionally, there are further constraints in the current practice environment. Presently, external network access is blocked, and I kindly request your understanding regarding this recording mode of conduct. If you observe the communication status between clusters, you will notice that internal to external connections are permitted, but external to internal connections are not possible due to the hybrid cloud configuration. One way to interpret this is as a configuration in a hybrid cloud scenario, where communication is allowed from the internal cluster to the external one, NKS, but not the other way around, from NKS to the internal open stack. Therefore, we will examine the setup where the service mesh is established from the OpenStack internal network towards NKS using service mesh. To configure this, you need to set up the kubeconfig in the internal OpenStack environment. Specifically, CTX1 should point to the OpenStack internal network, and CTX2 should be configured to point towards NKS. When installing the container platform, Helm is automatically included, so we can proceed with that. Next, install the STEP CLI to generate certificates. STEP is an open source tool that simplifies certificate generation. For mesh service interconnection using MTLS between clusters, you'll need to use the same certificate. Follow the guide to install STEP, and subsequently, install the linked CLI for the next steps. Through the previously installed STEP, generate actual TLS certificates using root certificates and to root certificates. Then you will be able to confirm the creation of CUS certificates and issuer certificates here. In this exercise, we will install all the linkered components using Helm, deploy the linkered CRDs to both clusters using Helm, then install the linkered control plane using the certificates created earlier. Then install the linkered control plane using the certificates created earlier. You can see where the certificates are used. To verify the linkered dashboard, you need to install the linkered viz extension. To access the extension dashboard from the web, you also need to deploy an ingress. So far, this has been the basic installation process for linkered. From now on, we need to set up a multi-cluster configuration through the service mesh and install the multi-cluster extension. To enable communication between clusters, you need to create credentials for each cluster in the other cluster. As mentioned earlier, since communication to NKS does not work with the internal network in OpenStack, credentials resources for OpenStack will only be created in NKS. Currently, we are installing the linkered multi-cluster extension on both sides using Helm. After installation, if you check the linkered multi-cluster namespace, you will see that the external IP is in a pending state. For Kubernetes services provided by managed services like NKS, their own CSPs automatically create and utilize load balancers. However, in the case of OpenStack, such functionality does not exist. Therefore, you need to install a meta load balancer, but in the current situation, Even if you provide an externally accessible endpoint using a metal load balancer, it won't be accessible from NKS due to policy reasons. We'll skip this part. If you check the linkered multi-cluster namespace from the NKS cluster, you will see the external IP. After confirming this, you need to create credentials in the NKS cluster for the OpenStack container platform's resources in the internal network. Then, when you check the multi-cluster status in OpenStack, it should be confirmed as normal. Next, to use the traffic split API provided by the linkered SMI extension, install the SMI extension. So far, we have completed the configuration of the linkered components required to set up the multi-cluster mesh environment. Now, let's move on to configuring the sample app. We will deploy the Hello World sample app in the NKS cluster. First, if you look at the YAML file, you'll see that the mirror.linkered.io exported field in the service section is set to true. With this setting, the same service is created on the other cluster that is part of the multi-cluster. Additionally, the deployment section has injection enabled. After deployment, you can see the service being installed in the NKS cluster. However, you will also notice that in cluster 1 only one service is created. And in the OpenStack cluster, a deployment corresponding to Hello World v1 is also deployed. This deployment does not have mirror settings, but only has injection. Using the previously installed SMI extension, we will deploy traffic split policies to distribute traffic 50-50 between the Hello World and Hello World cluster to services. Then, we will send curl requests from a sleep pod to check if the traffic is distributed correctly. Yes, that's how it works. You can find this script in the folder. If you look in the folder called linkered, you'll see that the explanations are provided in order. This part is not covered in the guide, but it's a script to install an Ingress controller on cloud. There are comments explaining the certificate installation process, making it easier to understand. Furthermore, the script contains commands for installing the linkered CLI, linkered CRDs, control plane, viz, and Ingress configuration. It also includes the multi-cluster setup, multi-cluster extension installation, and validation processes deploying extensions that distribute traffic, and another for deploying the SMI extension. Lastly, the YAML files contain the sample apps we are deploying. In the execute shell file, we will send traffic from the sleep pod to the Hello World service 100 times, with 8-second interval, to see how it's displayed. That concludes the explanation, and you can watch the practical demonstration in the video. First, let's take a look at the kube config settings. The cluster with A10xxx range is the OpenStack cluster, and NKS is a cluster whose server address is set to the domain. We named the context on the OpenStack cluster CTX1, and the NKS was named CTX2. It's important to have these context names aligned for smooth operations. Now, let's proceed to clone the Git repository containing the scripts we just discussed. Navigate to the TechEdge linkered folder, where you'll find the files. Provide execution permissions for the shell files. Let's start with the 0 Cloud Ingress shell file. The installation script within this file referenced in Cloud's official guide. We ran this file to deploy Ingress control to our NKS Cloud CDX2. Currently, you're viewing the contents of the one certificate.sh file. This script installs the step CLI for certificate generation. It's in shell format, so the installation happens collectively. Then, use the deploy.sh file to install the linkered CLI and deploy the components associated with linkered. The linkered components included a control plane and a dashboard to collect metric information and view dashboards, and extension called linkered viz to collect metric information and view dashboards. Finally, it also includes the deployment of Ingress rules to access the dashboard from the outside. Running this file starts the CLI installation. The CRD installation is complete and the control plane is installed on both clusters. The linkered viz extension is also being installed, including services like Prometheus for metrics collection. Deployment to the NKS side is currently underway. Finally, we deployed Ingress rules to access the dashboards associated with both clusters. We see this based on the namespace of each cluster. On the OpenStack side, we see the linkered and linkered viz namespaces, and the same is true on the NKS side. There were no installation errors, so we just verified the namespaces. Now, let's check if the Ingress settings are correct. We'll use this Ingress address for access. For OpenStack, you can access it using port 30772. Let's also take a look at the dashboard deployed on the NKS side. Being a managed service, it's automatically connected to a load balancer. By accessing the load balancer's domain address, you can view the linker dashboard deployed on the NKS side. Up to this point, we've successfully deployed all the core linkered components. Now, let's deploy a linkered multi-cluster extension to verify its multi-cloud functionality. If you look at the files, you'll notice we're deploying the linkered multi-cluster extension to both clusters using Helm. We wait for 40 seconds. We determine this duration after conducting a few tests. During this time, the clusters need to establish communication, and it takes a while as certain gateways need to be installed. We wait a bit and then proceed to extract credentials on the NKS side, and wait another 10 seconds. If, despite waiting, you encounter errors from the probe service, you can manually check by running the linkered multicluster check command. This should show that everything is working as expected. The installation of these resources seems to take a little over 10 seconds to complete. Now, let's proceed to install the SMI extension for using the Traffic Split API. We're using Helm again to deploy this extension. The installation is in progress. The installation is in progress. We've completed all the additional extensions and configurations necessary to verify the multi-cloud functionality. Now, let's deploy the sample applications. First, the YAML file for Hello World v2 to be deployed on NKS. Check if the service's mirror exported setting is true, and the deployment's injection setting is enabled. This will be deployed to NKS CTX2. Once deployed, let's check the resources labeled as Hello World v2 on the NKS. You'll find that Hello World v2 is installed. On the OpenStack, you'll see Hello World cluster to deployed. Since the mirror export setting was true, it was automatically deployed to the other cluster. Next, let's deploy Hello World v1 on the OpenStack cluster. Yes, you can see that Hello World v1 deployment pod is successfully deployed. You can confirm that both Hello World Cluster 2 and the newly deployed Hello World v1 are working properly. Now, let's deploy the traffic split policy. Unlike what was described earlier, during the actual practice, we'll distribute 70% of traffic to the Hello World deployed on the OpenStack cluster, and 30% to the Hello World cluster 2 on the NKS cluster. The deployment is complete. Lastly, let's deploy the sleep pod to generate actual traffic. After deployment, we'll use the shell script to send 100 curl requests every 2 seconds. When the sleep pod deployed on the OpenStack cluster sends curl requests to Hello World on port 5000, the traffic split policy will distribute the traffic to OpenStack's service v1 and NKSS's service v2 based on the defined percentages. You can observe that traffic is flowing correctly to v2 on the NKS and v1 on the OpenStack. You can also check this on the dashboard. In the service menu, you can see the success rate for outbound traffic to Hello World and Hello World Cluster 2. The metrics for Cluster 2 are collected on Cluster 2, so they aren't linked to the dashboard. You can observe that 18 requests are sent to V1 with a 70% setting, and 8 requests are sent to NKS with a 30% setting. The same view as on the dashboard can also be seen using the linkered visstat services command in the CLI. That's all for the prepared content. As Istio is planned to be applied to the container platform package, we focused on deploying a sample app using linkered in this session. We have plans to utilize various open source tools with domestic CSPs. The completed content will be continuously updated on GitHub, so your keen interest would be greatly appreciated. If you have any further questions or would like to learn more about our K-PaaS container, platform, and multi-cloud support, please feel free to leave a comment on K-PaaS portal website. Thank you once again, and we look forward to your participation in future TechEdge sessions.